Welcome to this problem-solving session. Today, we'll explore an exciting problem from the coding domain, problem number 139, titled Word Break. We'll break down the problem step by step, analyze various approaches to solve it, and discuss the trade-offs. Let's dive in and get started. In this problem, we're given a string S and a dictionary of strings called WordDict. The goal is to determine whether the string S can be segmented into a sequence of one or more words, where each word must come from the dictionary. Importantly, the same word in the dictionary can be reused multiple times when forming this segmentation. For example, if a word appears twice in the string, it can still be matched using just one entry in the dictionary. Additionally, you can assume that the dictionary does not contain duplicate words, so each word in WordDict is unique. The input string S is non-empty and only contains lowercase English letters, and the dictionary is a list of non-empty strings, each also made up of lowercase English letters. The output should be true if the segmentation is possible, and false otherwise. Now, let's walk through a couple of examples to clarify. In the first example, the input string is S equals LeetCode, and the dictionary of words is WordDict equals LeetCode. Here, the string LeetCode can be split into two substrings, Leet and Code. Both of these substrings are present in WordDict, so the segmentation is valid. As a result, the output is true. In the second example, we have S equals ApplePenApple and WordDict equals Apple Pen. In this case, the string can be split into three parts, Apple, Pen, and Apple again. Both Apple and Pen are found in the dictionary. Moreover, the problem allows us to reuse words from the dictionary, so it's perfectly fine to use Apple twice. Therefore, the output is also true. Let's look at another example where the segmentation is not possible. Here, the input string is S equals cat sand dog, and the dictionary is WordDict equals cats, dog, sand, and cat. While parts of the string, such as cats and dog, do exist in the dictionary, there's no way to segment the entire string into valid dictionary words. Specifically, the substring OG at the end cannot be matched with any word in WordDict. As a result, the output is false. This highlights the importance of ensuring every part of the string is accounted for in a valid segmentation. Finally, let's consider the constraints and edge cases for the problem. The length of the input string S can range from 1 to 10,000, and the size of the dictionary can be as large as 1,000 words. Each word in the dictionary can also have a length of up to 10,000 characters. Both the string S and all dictionary words consist only of lowercase English letters. When thinking about edge cases, consider scenarios like a single character string, which can only be segmented if that character exists in WordDict. Similarly, if the dictionary is empty, the output will always be false, unless the string itself is also empty. Another edge case is when the string contains repeated substrings. The solution must handle the reuse of dictionary words correctly. Finally, because of the constraints, handling very large inputs efficiently is key to ensuring good performance. To begin analyzing the problem, we can first consider a brute force approach using recursive backtracking. The intuition here is to try every possible way to split the string S into segments and check if each segment exists in the given dictionary, WordDict. At a high level, this approach works by iterating through all prefixes of the string and checking if a prefix matches a word in the dictionary. If a valid prefix is found, we recursively apply the same logic to the rest of the string. The algorithm starts with the full string, iterates through possible prefixes, and recursively solves for the remaining substring. While this approach is simple and intuitive, it has significant downsides. The time complexity is exponential, 2 to the power of n, because it explores every possible partition of the string, leading to many repeated calculations. Additionally, it requires n space for the recursion stack. While straightforward to implement, this method becomes impractical for larger strings due to its inefficiency and lack of optimization. A more efficient strategy is the dynamic programming approach, which eliminates redundant computations by storing intermediate results. The key idea here is to use a DP array, where DP, I, indicates whether the substring S, 0I, can be segmented using words from WordDict. To determine this, for each position I, we check if there exists an earlier position j such that the substring S, ji, is a word in the dictionary and DP, j, is true. This ensures that we only proceed if the previous segment is valid. The algorithm begins by initializing a DP array with DP 0 equals true, since an empty string can trivially be segmented. Then, we iterate through the string, and for each position, we check all possible splits. If we find a valid split, we update the DP array. Finally, the value at DP lens tells us whether the entire string can be segmented. This approach is much more efficient, with a time complexity of O(n) squared, due to the nested loops, and it uses O(n) space for the DP table. It avoids the exponential growth of the brute force method while remaining relatively simple to implement. Another approach to solving this problem is using breadth-first search, or BFS, which treats the segmentation task as a graph traversal. Here, each substring of S acts as a node, and an edge exists if a valid word in WordDict allows a segment to split correctly. This approach uses a queue to explore all potential substrings. Starting from the beginning of the string, we enqueue the starting index and try all possible splits. If a valid split is found, we enqueue the endpoint of that split. The process continues until we either reach the end of the string, indicating successful segmentation, or exhaust all possibilities. To avoid revisiting the same indices, we use a visited set. This method has a time complexity of O(n) squared, similar to the DP approach, as we are still examining substrings, and it requires O(n) space to maintain the queue and visited set. While BFS provides an alternative with comparable efficiency to DP, it often consumes more memory due to the additional data structures and can be slightly more complex to implement. Among the strategies discussed, the dynamic programming approach stands out as the most balanced solution in terms of simplicity, efficiency, and space usage. Unlike the brute force method, it avoids redundant computations by storing intermediate results in a DP table. Compared to BFS, the DP approach is easier to implement as it does not rely on extra data structures like a queue or a visited set. With a time complexity of O(n) squared and a space complexity of O(n), the DP solution is highly efficient for this problem. The fundamental insight that makes this approach work is recognizing that the problem has overlapping subproblems, such as repeatedly solving for the segmentation of the same substring. By leveraging the DP table, we can efficiently manage these subproblems, avoiding the exponential growth seen in brute force. Ultimately, the DP method is a robust, deterministic, and practical solution for handling both small and large inputs effectively. The word break problem requires us to determine if a given string, yes, can be split into a sequence of one or more space-separated words from the dictionary WordDict. To approach this problem, we start with a recursive backtracking solution. The idea is simple: if the string S is empty, we can immediately return true because there's nothing to segment. This serves as our base case. For non-empty strings, we explore every prefix of S. Each prefix is checked against WordDict to see if it exists as a valid word. For example, if the string is cat-sandog, we examine prefixes like c, ca, cat, and so on. If a prefix is valid, we recursively apply the function to the remaining substring. The goal is to determine if at least one of these recursive calls on the remainder returns true, which would indicate that the entire string can be segmented into valid dictionary words. If we can split the entire string into valid segments, we return true. However, if no prefix matches or none of the recursive calls succeed, we return false. There are also a few edge cases to consider. If WordDict is empty, we return false because there are no words to match against. Similarly, if the string S contains characters that don't exist in any word from WordDict, it's impossible to segment, so we return false. Now, let's discuss the computational implications of this approach. Recursive backtracking can lead to exponential growth in the number of recursive calls. For a string of length n, the time complexity can become O(2 to the power of n), as we explore all possible ways to split the string at each character. Despite this inefficiency, recursive backtracking is a straightforward way to exhaustively explore all possible segmentations of S. However, it does have limitations, especially for long strings or large dictionaries, as it will redundantly check the same substrings multiple times, making it computationally expensive. To implement this algorithm, we use some key data structures. First, the dictionary WordDict is converted into a set to enable O(1) average time lookups. This is crucial because we'll frequently check if a prefix exists in the dictionary. Second, strings are used to represent the prefixes and remaining substrings. Python's slicing capabilities make it efficient to create these substrings during the recursive calls. Let's look at the code. The function word_break defines a helper function called backtrack that takes the starting index of the substring we're currently examining. The base case is simple: if we reach the end of the string, we return true, as this means the string can be fully segmented. Inside the function, we iterate over all possible end indices to extract prefixes, checking each one against the dictionary. If a prefix is valid, we recursively call backtrack on the remaining substring. If one of these recursive calls returns true, we propagate that success back up. If no valid segmentation is found after exploring all possible prefixes, the function returns false. To optimize lookups, we convert word_dict into a set at the start of the function. The final result is determined by calling backtrack with the starting index set to 0. Analyzing the complexity, the time complexity is 2 to the power of n in the worst case, as each character in the string can create two branches, representing whether a word is included or excluded. The space complexity is n, which arises from the depth of the recursion stack. To address the inefficiencies of this approach, we can introduce memoization. By storing the results of previously computed subproblems, such as whether a certain substring can be segmented, we avoid redundant computations. This optimization significantly reduces the time complexity to n*m, where n is the length of the string s and m is the average length of words in the dictionary. Another powerful optimization is to use an iterative dynamic programming approach. Here, we define a Boolean array dp where dp I indicates whether the substring s I can be segmented into valid words. This approach eliminates recursion entirely and focuses on building the solution iteratively. Let's consider some edge cases to better understand the problem. If the input string is apple and the dictionary is empty, the output is false because there are no valid words to form the string. For the string cats and dog with the dictionary containing cat, cats, and dog, the output is true, as the string can be segmented into cats and dog. Finally, if the string is ABCD with a dictionary containing A, ABC, and B, the output is false, since the string cannot be fully segmented into valid parts. These examples highlight how the algorithm handles different scenarios and edge cases effectively. The solution for LeetCode problem number 139, word break, uses dynamic programming to determine if the input string s can be segmented into space-separated words from a given dictionary word_dict. The algorithm begins by converting word_dict into a set called word_set. This optimization ensures that word lookups are performed in O1 time. Then, a dp array is initialized with false values. The size of this array is len s plus 1. Each dp I represents whether the substring s0i can be segmented into dictionary words. Initially, dp0 is set to true since the empty substring is trivially segmentable. The main logic involves two nested loops. 1. The outer loop iterates over I from 1 to len s. For each I, we examine substrings ending at index I. 2. The inner loop iterates over j from 0 to I1 to check all possible prefixes of s0i. If the substring s(j)i exists in word_set and dp j is true, it means s0i can be segmented, so dp I is set to true. The algorithm short-circuits the inner loop using a break statement once dp I becomes true, avoiding unnecessary checks. Finally, the value of dp lens is returned. This value indicates whether the entire string s can be segmented into dictionary words. This approach has a time complexity of n², where n is the length of s. This arises from the nested loops in substring checks. The space complexity is n due to the dp array. Edge cases handled include an empty string s, which always returns true. A word_dict with no valid words, which ensures the function returns false unless s is empty. Repeated words in word_dict, which are efficiently handled using the set conversion. This is the Java implementation of the word break problem from LeetCode, number 139. The logic mirrors the Python implementation. It uses dynamic programming to determine if the input string can be segmented into valid words from the dictionary. The primary differences lie in Java's syntax, explicit type declarations, and the use of Java-specific collections like hashset for efficient lookups. The solution builds a Boolean dp array where dp I, indicates whether the substring s0I can be segmented. The final result is stored in dp s.length. We start with the input string LeetCode and the word dictionary containing LeetCode. First, we convert the word dictionary into a set for faster lookups, resulting in word_set equals LeetCode. Next, we initialize a dp array with a size equal to the length of the string plus 1. This array is used to determine whether the substring up to each position can be segmented into valid words. Initially, dp0 is set to true since an empty string is always segmentable. Now, we process the string using two nested loops. The outer loop runs from I equals 1 to the length of the string, and for each I, the inner loop checks every possible substring s, j, I, where j runs from 0 to I1. For I equals 4, the substring s, 0:4 equals leet. Since dp0 is true and leet exists in word_set, we set dp4 to true. This means the first part of the string can be segmented. Similarly, at I equals 8, the substring s, for :8, equals code. With dp4 being true and code in the word set, we set dp8 to true, indicating the entire string can be segmented. The final dp array confirms this segmentation process. At the end of this process, we check the value of dp8, which corresponds to the entire string. Since dp8 is true, it means the string LeetCode can be segmented into words from the dictionary. The output for this example is true. Now, let's consider another example where the input string is apple pineapple and the word dictionary contains apple and pen. Again, we start with the setup. The word dictionary is converted into a set, word_set equals apple, pen, and the dp array is initialized with a size of 14, corresponding to the length of the string plus 1. dp0 is set to true to represent the empty string. For the string apple pineapple, the outer loop iterates over the string's length, and the inner loop checks substrings. At I equals 5, the substring s, 0:5 equals apple. Since dp0 is true and apple exists in the word set, we set dp5 to true. This indicates that the first part of the string can be segmented. Moving to I equals 8, the substring s, 5:8 equals pen. With dp5 being true and pen in the word set, we set dp8 to true. Finally, for I equals 13, the substring s, 8:13 equals apple. As dp8 is true and apple exists in the word set, we set dp13 to true. The dp array reflects these updates, demonstrating that the string can be successfully segmented. Now let's analyze the example where the string is cat sandog and the word dictionary contains cats, dog, sand, and cat. First, we convert the word dictionary into a set, resulting in word_set equals cats, dog, sand, and cat. The dp array is initialized with a size of 11, corresponding to the length of the string plus 1, with dp0 set to true. In the outer loop, at I equals 3, the substring s, 0:3, equals cat. Since dp0 is true and cat exists in the word set, we set dp3 to true. Then at I equals 4, the substring s, 0:4, equals cats. With dp0 being true and cats in the word set, we set dp4 to true. At I equals 7, the substring s, 3:7, equals sand. As dp3 is true and sand exists in the word set, we set dp7 to true. Finally, at I equals 10, the substring s, 7:10, equals dog. Since dp7 is true and dog exists in the word set, we set dp10 to true. The dp array reflects these updates, showing how the string can be segmented step by step. At the conclusion of this example, we check the value of dp10, which corresponds to the entire string cat sandog. Since dp10 is true, it confirms that the string can be segmented into valid words from the dictionary. The output for this example is true. By following this dynamic programming approach, we systematically evaluate all possible substrings and efficiently determine if the input string can be broken down into words from the dictionary. Here, we analyze the time complexity of the solution, which is O(n²*m). To break it down, n represents the length of the string s, and m is the average length of the words in word dict. The outer loop iterates through all indices of the string s, which means it executes O, n, times. Within this, the inner loop runs from index j equals 0 to j equals I1. In the worst case, this inner loop runs O, n, times for each value of I, giving a total cost of O, n squared, across all iterations. Additionally, for each iteration of the inner loop, we check if the substring s, j, I, exists in the word set. Extracting this substring takes O, I, j, time, which in the worst case is O, n. Membership checking in the word set is efficient and averages to O, 1. However, because we compare this substring against words in the dictionary, the time required includes a factor of O, m, where m reflects the average word length. When all these costs are combined, the total time complexity becomes O, n squared asterisk m. The space complexity of the solution is determined to be O, n plus u. Here, n represents the length of the string s, and u is the total number of characters in WordDict, which is the sum of the lengths of all words. The dynamic programming array, or DP, is sized at n plus 1 to store the segmentation status of each prefix of s. This contributes O, n, space. Additionally, the word underscore set stores all the unique words from WordDict, and the memory required for this is proportional to the total number of characters in the dictionary, or O, u. Combining these, the total space complexity of the solution is O, n plus u. Now, let's analyze the best, average, and worst cases. In the best case scenario, the first word in WordDict matches the prefix of s, allowing the inner loop to terminate early. In this situation, the time complexity is still driven by the outer loop and substring checks, resulting in O, n asterisk m. For the average case, the inner loop only partially runs for each index I, and substring checks occur for a smaller range of values. Even with this, the complexity remains O, n squared asterisk m. Finally, in the worst case, every substring check fails until the last iteration, requiring the inner loop to fully execute for all values of I. This results in the maximum time complexity of O, n squared asterisk m. To put this into perspective, we compare it to a brute force approach that generates all possible substrings of s. This naive method requires O, 2 to the power of n, combinations, and for each combination, membership checking in WordDict takes O, m. Consequently, the brute force approach has a total time complexity of O, 2 to the power of n asterisk m, which is exponentially worse than the optimized dynamic programming solution with O, n squared asterisk m. The current solution incorporates several optimizations to improve efficiency. Dynamic programming is utilized to store intermediate results, which avoids redundant computations. Additionally, using a set for WordDict allows average time membership checks to be performed in O1, significantly reducing lookup costs compared to an alternative like a list. From a mathematical perspective, the time complexity is derived as follows. The outer loop executes O, n, times, while the inner loop runs O, n, times in the worst case for each index I. Extracting substrings and checking membership in the word set together take O, n, for each inner loop iteration. Multiplying these gives O, n, asterisk O, n, asterisk O, n, equals O, n squared asterisk m. On the space side, the DP array contributes O, n, and the word underscore set takes O, u, resulting in a total space complexity of O, n plus u. These optimizations and their mathematical backing demonstrate the efficiency of the dynamic programming approach compared to less sophisticated methods. When solving the word break problem, there are a few common mistakes to watch out for. First, many solutions fail to optimize overlapping subproblems. This happens when recursive solutions repeatedly solve the same substring without using memoization or dynamic programming, leading to exponential time complexity. For instance, if you're checking the string apple penapple with the dictionary, apple, pen, you might end up verifying the same substrings multiple times, which is highly inefficient. Next, improper base cases in recursion are another frequent issue. If the empty string or termination condition isn't handled correctly, you can run into infinite recursion or incorrect results. For example, the algorithm might fail to terminate even when no valid splits remain. Lastly, ignoring edge cases, such as strings with no valid splits or ambiguous overlaps in the dictionary, can lead to runtime errors or incorrect outputs. Consider a case like AAA with the dictionary, AA, AAA. Overlapping words can confuse the solution if edge cases aren't managed effectively. Another common pitfall is neglecting to sort the dictionary when using a greedy approach. Greedy strategies often fail if longer words are not processed first. For example, with the dictionary, cat, cats, dog, splitting cat's dog by prioritizing cat before cats leads to incorrect results like cat plus dog. This highlights why sorting the dictionary by word length is crucial in these cases. Inefficient string operations are another source of trouble. Repeatedly slicing strings, such as using s-i or s-i inside loops, can drastically slow down your solution. Substring operations are computationally expensive, and when combined with recursion, they can make the algorithm impractical for larger inputs. Optimizing these operations is key to improving performance. In interviews, this problem provides a great opportunity to showcase your ability to recognize patterns and optimize solutions. The task of breaking a string into dictionary-defined segments can be compared to solving a pathfinding problem, where each valid path corresponds to a word in the dictionary. Demonstrating how you transition from a brute force solution to dynamic programming is a great way to highlight your problem-solving skills. Dynamic programming is especially useful here as it avoids redundant calculations, making the solution much more efficient. Additionally, you should be prepared to analyze the time complexity of your approach. For example, the dynamic programming solution typically has a complexity of n squared, considering substring checks and dictionary lookups. Be ready to answer follow-up questions, such as handling overlapping words like in cat sand dog with the dictionary, cats, sand, dog, or optimizing for large dictionaries by using data structures like a tree. The concepts in the word break problem are closely related to several other LeetCode problems. For example, LeetCode 139, the word break problem we're discussing, focuses on determining if a string can be segmented into dictionary words using dynamic programming or recursion. LeetCode 140, Word Break 2, takes this a step further by asking you to find all possible sentences from the same string in dictionary. Another related problem is LeetCode 472, Concatenated Words, which challenges you to identify words in a list that can be formed by concatenating other words. Finally, LeetCode 131, Palindrome Partitioning, involves partitioning a string into substrings, but with the additional constraint that each substring must be a palindrome. These problems build on similar concepts and can help deepen your understanding of string manipulation and recursion. There are also alternative approaches to solving the word break problem, each with its own trade-offs. Recursive backtracking is simple to implement but inefficient without memoization, as it has exponential time complexity. Dynamic programming, on the other hand, is much more efficient, reducing the time complexity to n squared, while avoiding redundant calculations, though it requires additional space for the DP table. Using a tree for faster dictionary lookups is another option, especially useful when the dictionary is large. However, it requires pre-processing the dictionary and consumes extra memory. Finally, a breadth-first search (BFS) approach can be used to explore possible splits level by level. While BFS guarantees the shortest path in terms of splits, it can be slower than dynamic programming for large inputs. Each approach has its strengths and weaknesses, and the choice of method often depends on the constraints and requirements of the problem. Great job! We've successfully tackled the word break problem, exploring both brute force and dynamic programming approaches. Remember, dynamic programming is a powerful tool for solving problems with overlapping subproblems. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!